researchers doing their thing. And last year at Hack in the Box, there was a presentation, Bugs and Kisses, that showed how easy it is to write a BlackBerry spyware app and use the same kind of Trojan tricks that work all too well on the Windows platform to that same class of people. It works on the BlackBerry. At Veracode, we did our own research kind of in parallel, and at ShmooCon, Tyler Shields, one of our researchers, released the Trojan that he wrote, and he released the source code too, so everyone could see how simple it was. He's not even a Java programmer. He just picked up enough Java so that he could write a BlackBerry Trojan. We distributed the source code so people could see all it is calling the APIs. It's just saying, get the GPS location, wait a while, send it out over a TCP/IP socket somewhere, send it out over SMS. It's really trivial stuff. So the one, thing the one denial or theoretical thing I've been hearing, because this is the phase we're in right now with mobile Trojan spyware. And I know there's a panel about this tomorrow, and there's a talk about it later today. So I'm interested in that, what other people have to say. But we're really in this phase now where it's theoretical, right? People saying, no, it's theoretical, it's not going to happen. One of the things I hear is people say there's too many platforms. People aren't going to write, BlackBerry Trojan and an iPhone Trojan and an Android Trojan and a Symbian Trojan. Well, maybe they're not, but each of those platforms has, 25 million to 50 million users out there. That's a pretty big target base with just writing it for one platform. So I don't buy that at all. The attack automation hasn't happened yet. We haven't seen the widespread attack automation here. But we're going down this curve, right? It's the technology's, been being adopted for the last 2 or 3 years. People are buying these things like crazy. So I'm hoping that we don't see the exact same thing that happened with Windows malware happen on the mobile platforms. Because it would just be silly to have, a decade of learning, more than a decade of learning with Windows malware just be reproduced 10 years later. So now I want to take that stuff and look at it and say, what can we learn from those examples and sort of that time value. And one thing I thought about was, the attackers, when they attack the platform, have so much more knowledge about the vulnerabilities in the platform, the security model of the platform, than the designers did when they built it. Because they have the benefit of doing this 2, 3, 4 years later. So there's sort of a built-in problem with shipping, technology that has core design problems in it. That the attacker can take advantage of all that stuff, and what are you going to do about it? Right? That's the question. What is that? What is the platform provider or the person writing the software going to do about this fundamental problem of they shipped design defects? And I don't think there's much you can do. And that's why I think we have a big problem. And to some degree here, it varies by technology, but sort of the more frozen the technology, I should come up with a better word, but it's the worse this effect is. Sort of if it's a hardware platform or an operating system platform, you can't really change the design of that very well. Like, how do you change Wi-Fi? How do you change the Windows operating system? You can't really change a lot of the fundamentals. I mean, that's why the Windows malware or Trojan problem is so bad. Because there's a fundamental problem with being able to just click on a link and install an arbitrary piece of software and have it execute on the system. It's fundamentally broken. So the more solid or solidified the design is, the harder it is to update it. It's harder to take changes, and even if you do make those changes, they take a long time. I mean, look at Windows. Every release has gotten a little bit better at kind of informing the user and not letting the user install a Trojan running as a system, right? You know, they made a little bit of progress with XP, Service Pack 3, a little bit more progress with Vista and Windows 7, but the problem is still there. It's a little bit better. But it's because they need to have backwards compatibility to this fundamental system that they put out in 1995. So, I don't know if this is exactly right, this hierarchy, because I was thinking that maybe servers are a little bit more solidified than clients, but certainly hardware is hard to update the design, and operating systems are hard to fundamentally change. Client and server, you know, app level stuff's a little easier to change that. And cloud is really the easiest to change because no one has to install anything, right? You don't have to run around installing anything. It just happens in one place by the cloud provider. So the ability to react quickly once you realize something is wrong is definitely a benefit that you want to take advantage of. I think cloud can take advantage of that. So I don't know how many people have heard of the OODA loop, or some people call it the OODA loop. But the concept is, this is a decision loop. And Colonel Boyd was in the U.S. Air Force. He was a fighter pilot. But he didn't really spend much time being a fighter pilot. Really what he was a military strategist. And in the 60s and 70s, he studied air-to-air combat. And he studied what allowed one of the adversaries to prevail. And what he did was he came up with this concept of how you go from observing something to acting on it. And he realized that every organism, every individual does this constantly as they react to their environment. Organizations do this too. So first part of it is you observe, get some new information, you observe someone's coming at you, or you observe some new object shows up. And then you take that information and you orient that information into the body of knowledge and rule set that you already have, so you can start to make use of it. Then you have to come to a decision, and then you act on it. Right? And so this is the loop that happens as a fighter pilot is flying around and sees something on his radar, or sees a missile coming at him, or sees a plane, and he has to react to this. So you can imagine, soldiers, a platoon of soldiers acting as a unit, as an organization, getting inputs and coming together, orienting, and making decisions and acting. The thing that Boyd did when he was studying this, he realized that the time domain is the most important part of this. It's how quickly you can go from observation to action. And that was his key insight, that said if you could go from observation to action quicker than your opponent could, you're going to win the battle. Because what happens is, you've already made an action, and and before the opponent has been able to act, so he's observing you doing something before he's able to act on the old observation. And so he came up with this concept saying, getting inside the attacker's OODA loop. If you can go through your cycle faster, you're going to win. And so you can see how this would work in a military scenario. And the time domain, it is the most important factor. You could have more numbers on the battlefield or bigger guns than the other guy, but if he's faster, if he's able to observe and take actions faster, he's going to win. There was a study done on playing chess, where you can take half the pieces off the board, but if you allow that player to make 2 moves for every 1 move, even though he's got less numbers, less capability, but he's able to make more moves, he'll win, no matter what level the other player is. And so we can think about this with how we're trying to defend ourselves and how the attackers are behaving with security systems, with launching their attacks, and us launching our defenses. You know, we need to think about the time domain, right? The time domain over this, you know, as the technology is unfolding. So the simple rule is fast Buddha is life and slow Buddha is death. Oh, there's one more example from business I want to talk about was Toyota and Honda were looking at the way GM was coming out with their products in the 80s. And someone had, you know, read Boyd's book on the OODA loop, and they realized that GM was coming out with new products every 3 years. They had a 3-year cycle where they would, you know, survey the marketplace, decide what kind of car model and what features it needed to have, and it would take them 3 years from then to come out with the car. And so what Toyota and Honda did was, they said, well, what if we did one simple thing? We designed our product introduction to be 2 years. So we would, you know, observe the marketplace, and we would come out with our car in 2 years. So now Honda and Toyota are coming out with a car, and GM's car is basically already seems a year dated. And now GM is having to react to what Honda did a year ago when it does its next cycle. And then all of a sudden, Honda and Toyota have come out with their second 2-year cycle, and GM's only 1 year into its second cycle. And you can see how this multiplies over time to give a competitive advantage. So this is this can be applied to a lot of scenarios, and I like to, you know, apply it to security. Look at how this is happening on different levels. So if you have a reactive model, if you ship vulnerable technology at a core level and you have to react to that concept, it's only going to work if your OODA loop is faster than the attacker's OODA loop. To have a reactive model where you're reacting slower than the attacker is able to react is dead from the very beginning. So, you know, a data point from this year, McAfee found 10 million unique malware samples in the first half of 2010. And they said that there were 10,000 Kubernetes variants per month. This is what the antivirus is reacting to. This is what the attackers are doing. They're observing, you know, what's working